Good evening, everyone. My name's Eric Magno, and I'm here to present my capstone presentation entitled Forecasting Dengue Incidence in Davao City Using Climate Data and Time Series Analysis. So, if you guys didn't know, dengue is the fastest spreading vector borne disease in the world. And in 2019, the Philippines actually had its historically most number of cases with 430,000 cases. Although this number decreased in 2020 to 60,000 cases, I believe dengue is still a dangerous disease that needs to constantly be monitored and put into public awareness. Some quick facts: the 5-year average cases of dengue in the Philippines is 185,000, and dengue has no treatment, but the disease can be early managed. So here we have the DOH's National Dengue Prevention and Control Program, and these are the 6 components of that program. As a data scientist, 2 main points of interest I found easily accessible are case surveillance and outbreak response. So the goal of this project is actually the prediction of dengue outbreaks to allow for early response. If we are able to detect spikes in dengue cases early, we are able to respond better to outbreaks. We also create an opportunity for public health authorities to properly adjust to outbreaks in terms of preparation and creating public awareness. Here's the methodology of the project. First is data gathering, where we want to get the dengue cases and climate data. Then we want to clean the data to fit them into a time series index. Exploratory data analysis allows for visualizations. We have feature selection, in which climate data and associated lags are determined. Modeling, so we used Arimax and Profit in this project, as well as model evaluation. So these would be the RMSE of predicted and actual cases. So here are my 2 data sources. First is Pag-asa, which provided me with daily climatic data from 2009 to 2017 for Davao City. These would be rainfall, Tmax, Tmin, Tmean, relative humidity, wind speed and direction, and station pressure. We also have data from the DOH, which provided me with dengue cases in Davao City by morbidity week from 2009 to 2017, and these would be aggregated by district. So if you check out the Streamlit that that's provided, we can actually see a heat map of dengue cases by district in Davao City from 2009 to 2017. You're also able to click each district number to see the population and the name of the district. Next up, we have dengue cases by morbidity week. Here we can actually see the number of cases in each time period from 2009 to 2017. 2 things I want to take note of right now are there seems to be a spike in dengue cases around the July to August mark, or the 7th month. And there also seems to be a spike every 2 years. So 2012, 2010, 2012, 2014, 2013 as an outlier, and 2016. So this seems to indicate there is a annual seasonality, as well as a biennial seasonality, or every 2 years as well. Next, we have the seasonal decomposition of dengue cases, in which we can verify there is actually a seasonal component to the dengue cases. Next up, we have the correlation matrix of climate data. Here we can see which features are highly correlated. And for simplicity, we actually narrowed down the features to rainfall mean, P-min, P-mean, RH mean, and wind speed mean. I also use studies on climate data for dengue prediction in order to determine which climate features I wanted to use. So we can see that there's actually a study in which climatic factors, rainfall, and maximum temperature were significantly correlated with monthly dengue cases, as well as another study that indicated that relative humidity and rainfall significantly contributed to the impact on dengue transmissions, as well as relative humidity highly correlating with a 2-month time lag. So it shows that time lags can also be used. Next up, let's discuss the 2 models that I decided to use. So first off is Arimax, in which we can say that climate data can be used as exogenous variables, as well as Prophet. We can also actually use climate data as regressors, but we did not use it for this project due to time constraints. Next up, which parameters we have to tune for both models. So for our Emacs, we have the P, D, and Q parameters, which are the autoregressive of P, D for differential, and Q being the moving average parameter. For profit, we actually tune the seasonality as well as the trend or growth, as well as holidays, which isn't really relevant to this project. We also see whether or not we can require the data to be stationary. For Arimax, this is actually a requirement, while for profit, it's not necessary. Uh, Briefly talking about stationarity, what it means is that for each period of the time series, the mean, standard deviation, and variance should be constant. So one of the ways we can test this is the augmented Dickey-Fuller test. So these are the confidence intervals for my particular time series as well as the score that I got. As you can see, it's lower than the 1% up to 10% confidence intervals, as well as the p-value is shown, which shows how relevant this score is or how confident we can be with the test. So we can assume that the series is likely stationary. Next up, we have how we tune the ARIMA model. So I actually used a grid search approach for comprehensiveness, and we can see the ranges for which I tuned the P, D, and Q parameters 0 to 3, 0 to 1, and 0 to 3. And here we can see the best model or the best parameters for the ARIMA models, as well as the RMSE score that I got using walk forward validation. And we can see each uh, prediction interval I used, 1 week, 4 weeks, and 12 weeks ahead. Next, we can see the feature importance of climate data I used. So I actually tested them out with the best model per prediction interval with a lag of 0 to 12. I also used a grid search approach similar to the last slide. So we can actually see that the RMEC scores with each correlated climate data feature, and T mean seems to be the most relevant across all prediction intervals. Next up, we have the Arimax model tuning. So actually, the X in Arimax stands for the exogenous variables part. So this would be including the climate data features as opposed to a standard ARIMA model. Here we can see a dictionary of all the climate data features I use. So these would be the top two lags per climate data feature for each prediction interval. Here we can see the dictionary of the most relevant climate features and the best score that we were able to get. So none would indicate that the feature was not used, and here zero would indicate that a lag of zero was used. Next up, we have the profit model tuning. So here I actually used an intuitive approach. So I assumed a logistic growth for this model since there seemed to be a natural floor and cap for the number of cases. Here I used a floor of 10 and a cap of 500 as well. I used multiplicative seasonality because using additive seasonality, we were actually getting a result of negative cases for some time periods. I also use a biennial seasonality with these parameters for your order 5 to 25 and prior scale 10 to 25, in which I use documentation for the default parameters as well as standard approaches to tuning these parameters. Biennial seasonality indicates an outbreak every 2 years. And the annual seasonality was also added with these for your order parameters. This part is indicated by the outbreak around July to August, which is the rainy season in Davao City. Same thing, we also have the RMSE scores for each. So finally, we can compare the results for Arima, Arimax, and Profit across each prediction interval. We can actually see that Arimax performed the best for 1 and 12 weeks ahead, as we can see here, while Profit performed the best for 4 weeks ahead. One thing to note is, however, so these are the graphs that I was able to get. So red being the predicted values, while blue being the actual cases of dengue. So if we actually look closer, we can see that Arimax is actually able to predict values closer and finer compared to Prophet, while there seems to be a small delay 1 week ahead for predicting the outbreak. And if we look at the 12 weeks ahead, Arimax is actually not really able to predict this outbreak in time, while Prophet is actually able to pretty accurately pretty accurately predict when this outbreak will occur. So if we look at the conclusion, Arimax seems to be a more accurate time series model in terms of RMSE as a metric 1 and 12 weeks ahead. Despite this, Prophet predicts more accurately 4 weeks ahead. Prophet is also able to more accurately predict when a large outbreak will occur for longer casting intervals. Prophet is so the most relevant conclusion is that Prophet is able to successfully predict the when of dengue outbreaks in Davao City. Some recommendations I have is that we should explore more meta models for dengue incidence prediction. So if you look at studies, LSTM, which is a recurrent neural network, seems to be the most used model. We could explore using climate data as regressors for Facebook profit, explore using more current data for both dengue cases and climate. So some more applicable recommendations we have are that we can create models that are able to successfully capture the scale of outbreaks. So if you look at the last slide, we want to be able to overestimate the number of cases so that we can predict the scale of the outbreak other than the when. And we can create a pipeline using running morbidity week cases and weather forecasts. So a bonus slide is comparing neural networks actually to the same use case. So we can see that stochastic gradient descent with backpropagation neural network, backpropagation with genetic algorithm neural network, and generalized regressive neural networks. We can see that neural networks actually dominate this dengue incidence prediction use case. And we can maybe infer that maybe neural networks work better for dengue incidence prediction. So that's the end of my presentation. Thank you. And if there are any questions, feel free to ask.